Welcome students. In this video, we're going to talk about hybridization. For hybridization, you probably remember very basic material from general chemistry, essentially how to determine if a certain atom has an sp, an sp2, or an sp3 hybridization. I want to go a little bit more in depth here and talk about how and why hybrid orbitals form, and then we can recap the same ideas from general chemistry as well. So let's start our discussion with methane, which is CH4. Here I have a picture of the structure of methane. And what I notice about this picture is that all of the bonds are the same length and all of the bonds are equal distance from one another. So they're all 109.5 degrees apart. Let's take that idea and keep it in the back of our mind as we talk about carbon's electron configuration. When we look at carbon's electron configuration, it has two unpaired electrons in the 2p. And normally in valence bond theory, what happens is your unpaired electrons overlap with another orbital that has unpaired electrons, meaning that you would form one bond with this orbital and one bond with this orbital so that you would have two bonds. But wait, didn't we just say up here that carbon forms 4 bonds? We have a problem that carbon can only form 2 bonds according to its electron configuration. These bonds that we're considering, will they be the same size as one another? Yeah, because a 2p orbital and a 2p orbital will both form the same size bond as with respect to one another. Will they have the same energy? Again, yes, but will they be 109.5 degrees apart? No. And do I have the right number of bonds? No. So there's some problems here where the theory doesn't match what we see in real life. Let's imagine that we gave carbon some energy, and when carbon has some energy, it creates an excited state. And in its excited state, it takes one of the electrons, this one, and pops it up to a higher energy orbital. So now what we have is 4 half-filled orbitals. So now we have the opportunity to make 1, 2, 3, 4 bonds. Great. Will these bonds be the same size? Well, 3 of the bonds would have a 2p orbital, and 1 of the bonds would have a 2s orbital. And so, no, they can't be the same size because an s is a sphere, a p is a dumbbell. They're not going to end up having the same size orbital when they overlap with a hydrogen. Will they have the same energy? No, because over here, energy increases, and so the 2s orbital is not the same energy as the 2p orbital. So a bond from the 2s and a bond that involves a 2p are not going to be the same energy. Will the orbitals be 109.5 degrees apart? No, one's a sphere, and then the 2p's are 90 degrees apart. So we have still a lot of problems with the idea that we know this exists, but our theory isn't showing the formation of this tetrahedral structure where all of our bonds are the same length, they're the same energy, and they're 109.5 degrees apart. What do? Well, we come up with a new explanation, and the new explanation is hybrid orbitals. Hybrid orbitals are a mixture, right? That's what hybrid means. What's happening is we're taking atomic orbitals that you're used to, the s, p, and d orbitals, we're not worried about the f, and we're blending them. These new orbitals that we make after blending are still atomic orbitals. It means they belong to the atom. What happens is the 1s orbital is representing your core electrons, and we don't touch those. Right? So those are your core electrons. Over here, these, and remember we're just talking about 1s, 2s, 2p because we're talking about carbon. It is organic chemistry after all. Right? These are your valence shell. You have your core electrons, you have your valence shell. What happens is you take some number of your S and your P and your P and your P, and you blend those together. And after you do the blending, what you get is hybrid orbitals. Let's go through the creation of the sp3, the sp2, and the sp hybrid orbitals. Look at what blends, look at what's left over, and talk about how this ends up relating to what you need to know in organic chemistry. When we talk about sp3 hybridization, this is probably our most common, and our sp3 hybrid orbital has a shape that looks kind of like the p orbital, except one side is a little bit bigger and more spherical. That's the best I can draw. So what happens with our sp3 hybrid orbital? How does it form? Well, remember our 1s is going to be our core electrons. And we're going to only consider our second energy orbitals. And let's do this in the context of carbon. So we have an excited state electron configuration for carbon. And what will happen is we will take the S and all of the P's and we'll blend these. And we can blend them because these S and P orbitals are just mathematical functions. And so blending is just averaging. So we take these and we average them. And when we average them, we get 4 new orbitals. So if you put in 4 orbitals into the blender, you get 4 orbitals out. So now we have 1, 2, 3, 4 orbitals that are all the same energy, so they're degenerate. And we're calling them sp3 because they came from 1 S and 1, 2, 3 P's, right? So that's where we're getting that name from. The 1s orbital isn't touched, right? Nothing happened there. It's still the core or electrons. It wasn't involved in bonding, so it doesn't get hybridized. When we take these sp3 hybrid orbitals, all 4 of them, and we put them on top of one another so that their nodes align, what you get is this structure over here, where the circle in the middle is where the nodes are lining up. And then the larger red lobe is what I tried to draw up here. And then the teensy white lobe is the smaller side of the sp3 hybrid orbital that most textbooks end up leaving out. So don't be surprised if you don't see that lobe anywhere. And now we can start to see that when these get arranged, they're all 109.5 degrees away from one another. They're all the same length, which means they're also going to be the same energy because the orbitals are the same shape. So now we have a reason to say sp3 hybridization, that solves all of our problems. Let's look at the structure of ethane, which is the second simplest organic compound there is. I want to bring your attention to the bottom right-hand side of the screen where you see the structure for ethane. Notice how you have these bonds that are dashed and then some bonds here that are wedged. Those dashed bonds mean that those hydrogen atoms are going behind the plane of the page, and the hydrogens that are wedged are coming out at you. And so this is just our way to try to illustrate that 109.5 degree bond angle on a 2-dimensional sheet of paper. Now let's look at the orbitals. So on the left-hand side of this page, I have the sp3 hybrid orbitals for ethane. Here is an sp3, an sp3, an sp3, an sp3 for one of the carbons of ethane. Remember, those white lobes are just the little other side of the sp3 hybrid orbital, and most textbooks will leave them out. The other side of this structure has another carbon molecule or atom that I've highlighted the two different carbons in ethane two different colors. The carbon on the left, those sp3 hybrid orbitals are blue. The carbon on the right, those sp3 hybrid orbitals are yellow. And then what we're trying to illustrate right here is when those orbitals overlap, the sp3 from each carbon, they end up forming a sigma bond, right? So this is a sigma bond, carbon-carbon sigma bond, right, from two sp3 hybridized orbitals. Then the remaining orbitals end up overlapping with a 1s for each hydrogen. These are also forming a sigma bond. This is a carbon-hydrogen sigma bond. So even though these pictures are really confusing, I'm going to keep showing them to you with the hope that they end up making a little bit of sense, so that we can start to imagine the orbitals that are creating different bonds. Now let's look at sp2 hybridization. For sp2 hybridization, we're going to change our structure from ethane to ethene. And in ethene, notice how now we have a carbon-carbon double bond. Let's continue to start this process with our excited state electron configuration for carbon. We have a carbon in our ethene, and it doesn't matter if you choose the one on the left or the right, that has 3 electron groups around it. In general chemistry, you might have called this electron domains, electron sets, maybe you called it steric number, but there are 3 electron groups. If you have 3 groupings of electrons, then you need 3 orbitals in order to create this future structure of trigonal planar. Remember that these core electrons are not involved. What's going to happen is we're going to choose S and 2 of the P's, and we will blend those. And when those are blended, you end up with sp2 hybrid orbitals that are all the same energy. I blended 3 orbitals, I get 3 orbitals out. The key is you didn't use one of the 2 p orbitals. So guess what? It's still there. So one unused p orbital is still present, and that is imperative. And it's imperative because that's what forms the pi bond. Let's look and bring our attention down to the bottom right-hand corner where this diagram is. This is showing our sp2 hybridization where carbon is in the middle here, right? That's the nucleus of carbon. We have an unhybridized p orbital right here. And that unhybridized p orbital is still present, it still has an electron in it. Then the red orbitals are going to be your 3 hybridized sp2 orbitals. And it's difficult to see in the picture, but they're meant to be 120 degrees apart. So these are your hybrid orbitals that are sp2. Let's look at how these come together to make ethene. I've got the same picture in the upper left-hand corner as I did in the last slide. Remember that this is your p orbital, this is your sp2, sp2 and sp2. What happens when you have one carbon overlapping with another carbon is this. So here's one carbon, and here's the orbital set for another carbon. Remember, the nucleus for the carbons are where I'm drawing these green dots. This middle overlap is a carbon sp2 hybrid orbital with another carbon sp2 hybrid orbital that make a sigma bond. Over here, This is showing a carbon sp2 hybrid orbital with a hydrogen 1s orbital. It's also making a sigma bond, where this abbreviation that I'm highlighting in blue, kind of like the circle with the tail, that's the letter sigma, the lowercase letter sigma. This is showing the sigma bonds that are forming for ethene. Where's the double bond come in? What happens in the double bond is your p orbital, it's one p orbital, here's our second p orbital. They get close enough that they overlap. So there's an overlap here and there's an overlap here. P orbitals are special because they overlap above and below the nodes. That's what makes a pi bond different than a sigma bond, right? Your sigma bond was when you chop the bond, you see a circle. A pi bond has overlap above and below the nodes. Now, clearly my picture doesn't actually show my two p orbitals close enough that they're actually touching, but that's just an issue with the drawing. Because if we tried to put them close enough that they were actually touching, it'd be really hard to distinguish where the sigma bond is. So a lot of times what people do is what I have on the bottom right-hand side of the screen. In this case, we've drawn out all of the sigma bonds and we're just focusing in on the p orbitals. And so again, if these or when these p orbitals overlap, and this green part that I'm drawing in is meant to say, hey, these are close enough to overlap with one another, they end up forming that pi bond. So that unhybridized p orbital is imperative. It is what creates the pi bond for these structures. Now let's transition into triple bonds. For triple bonds, that's where we experience sp hybridization. Ethine looks like this. In ethine, now your carbon has two electron groups around it. So your two electron groups for carbon are going to need two equivalent locations to live. You need to hybridize two orbitals. If we go back to our excited electron configuration for carbon, what we will do is we'll take the S, the 2s, and one of the 2p's, and we'll blend those. When we blend, we end up with an sp hybrid orbital, and we have two of them. Because we put in two orbitals, you get out two orbitals. And then we have two unhybridized p orbitals. And remember the 1s, right? This one doesn't matter. This is a core electron. It didn't get used. It's not used in bonding. So we end up with a different situation now where I have sp hybrid orbitals here and here in the bottom right-hand corner. These are my hybridized orbitals. And then we have two p orbitals that were unhybridized. And these two p orbitals are 90 degrees apart from one another. Right? One is along the y-axis, the other one could be along the z-axis, but they're 90 degrees apart from one another. What ends up happening is whenever you have a p orbital on one atom and a p orbital on another atom and they overlap, that's one pi bond. But now you have two p orbitals. You can have two areas of overlap. That's where you get the fact that you have 1, 2 pi bonds and 1 sigma bond for your ethine. Is that whenever you have one p orbital, that can make one pi bond, but you have two unused or unhybridized p orbitals. Now, we could try to draw the picture of this like we have for ethene, but it gets really overwhelming really quickly. Instead, we'll wrap up with a little bit of a trend that's going to help us when we get to resonance in a later video. Just a quick reminder from general chemistry, the relationship between bond length and strength. If we compare ethane, ethene, and ethine, what we're seeing here is a single bond, a double bond versus a triple bond. And let's notice that the bond length gets shorter as we end up adding more attachments, right? So ethane is the longest of the set, and this is the shortest of the set. If we look at bond energy, ethane is the easiest bond to break. That carbon-carbon bond is the weakest bond energy, and ethane is the strongest. So this one is weakest, and this is strongest. Triple bonds are shorter and stronger than single bonds. Single bonds are longer and weaker. So if we look at the top of this and we say, as bond length increases, bond strength decreases. And this is just an important idea to have in the back of your mind when we dive into resonance, which will happen a little bit later. Let's wrap up and talk about what you should be able to do. You should be able to look at an atom and determine its hybridization. We'll work more on that in a subsequent video. I want you to be able to look at a molecule and decide which orbitals are making a bond. And I want you to know that when you have pi bonds being formed, that those are formed from p orbitals overlapping above and below the nodes, whereas sigma bonds are formed in such a way that when you chop them, they make a circle. Then finally, knowing the relationship between bond length and strength will help us when we get to resonance. Thanks so much for your attention. I'll see you in the next one. This is Katoni signing out.